Okay, so this is section 6.9, the last section before the quiz. And as I was saying, tomorrow should be the quiz over 6.5 through 6.9. But with everybody's schedule last week and the snow day, what I think I'll do is give tomorrow a work day, and the quiz will be Wednesday. So if you've got any concepts that you're struggling with, tomorrow is your chance to get help. Okay? And again, posters, if you don't want your poster, then I will throw it away. If you want to correct it, then take it today. Otherwise, they're going in the trash. Okay, so this section is awesome. Yes, because this is where everything we've been working toward is going to come together. Okay, and what we've learned so far is with our long division and our synthetic division, we've learned the process of how to use those tools to find solutions, to find whether or not what they give us is a factor or a solution. And what if it's a solution, what does that mean on the graph? If I get a solution, solution to be -4, and I were to graph that polynomial, what does -4 tell me?
-4 tells you where you're going to start.
No. And when we've solved quadratics, those solutions are what? There's like 2 or 3 different synonyms. Zeros, roots, right?
Yeah.
Solutions, what does it tell you? Which intercepts?
Y and X.
X-intercepts. Where it crosses the x-axis. Okay? So what I think we'll do is we're going to just use a problem, and I'm going to use one as an example here. Find what I want. X to the 5th minus 4x to the 4th minus 18x cubed plus 38x squared minus 11x minus 6. Okay, so in this section, we're going to learn how to find the solutions to a polynomial like this. In the last couple of sections, what we did is they gave us a factor, and we showed either in long division or synthetic division whether that factor was in fact a solution, like it didn't have a remainder. Right? Now, they aren't giving us any possible solutions, so we have to figure out what possible solutions there might be. And to do that, we're going to use something called the rational root theorem. Rational meaning something that can be represented by a fraction. Root meaning the zeros, the solutions, where it goes through the x-axis. Okay? And then theorem, just theorem. So it's the rational root theorem. And what it's going to do is tell us all possible solutions. If it's not in the list that we find using the rational root theorem, it's not a possible solution. So we're going to find all possible solutions. It doesn't mean every one we find will be a solution, but we've narrowed our list down to just a smaller group of numbers. Instead of an infinite number of solutions, we're going to be able to narrow it down. It's got to be in this list. Does that make sense? Okay. To do this, you find all possible factors of the constant and all possible factors of the leading coefficient. All possible factors of the constant, all possible factors of the leading coefficient. And to use the rational root theorem, you're going to make a fraction. In the numerator is all your possible factors of the constant, and in your denominator is all possible factors of your leading coefficient. Okay? So looking at -6, what are possible factors of -6? Yeah, plus or minus 1. Plus or minus 2, plus or minus 3, plus or minus 6. And the reason I say plus or minus, it could be 1 and -6. It could be -1 and +6. It could be +2 and -3. It could be -2 and +3. So we have to put the plus or minus in front, because it could be either sign. Okay? So our possible factors of -6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Those are possible factors of -6. With me so far? Possible factors of my leading coefficient. What is my leading coefficient? 1. I love it when my leading coefficient is 1. Okay, the reason is I put plus or minus 1 in the denominator. Does the denominator even have to be there? No. So I know when the leading coefficient is 1, my possible roots will never be a fraction, which is always a great sign for me. So I know I'm not going to have to do synthetic division with a fraction in the box. Yeah, which we may have to at some point. Yes, but this problem, because it's a leading coefficient of 1, I can do my happy dance because I don't have to do any fraction work. It's all going to be just integers. Okay, so now I've figured out my possible rational zeros are going to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Okay, I've just narrowed the universe of numbers from infinity down to 8. Because positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, positive 6, negative 6. That's 8 numbers that are possible zeros. Okay, so now instead of the book telling me, check this number and see if it's a 0, I've just made the list myself. These are the numbers I'm going to use to see if they're zeros. With me so far? Okay. For me, I usually start at the left and just work my way right, because 1 is the easiest number to use synthetic division with. Okay, so I'm going to start with positive 1. It's going to go in my box. Remember to do synthetic division, I'm just using the coefficients. And I don't have any placeholders. I've got numbers in all my placeholders, so that's nice. So my first number is 1. So I can fill this out. Negative 4, negative 18, 38, negative 11, negative 6. Okay, so I'm ready to do synthetic division. Yep. Drop the 1, multiply. Add, multiply. Add, multiply. Add, multiply. Add. This is like happy day. My very first choice ended up being one of the solutions. It's awesome. No? Okay. Sometimes you have to do this multiple times until you find one that works. Okay, let's interpret what I have left. I started with x to the 5th. I divided it by just an x minus 1 really is the factor, right? So my answer now should be an x to the 4th. So this, if I wanted to write it, I'm not going to, but if I wanted to write it, 1x to the 4th minus 3x cubed minus 21x squared, 17x plus 6. Okay, so I could rewrite it, but I already have it written here. So what's easiest for me now is I need to find, I've got an x to the 4th. My goal with synthetic division is get it down to x squared. Why? Why wouldn't I get it down to the whole thing? Why just x squared? Not necessarily. Do we know how to solve x squared problems? Quadratics. We factor it. Quadratic formula. We can, once it's to an x squared problem, a quadratic, I know how to solve that. That was all last chapter. So if I can get this problem down, how many times do I need to do this and find a 0? I started with x to the 5th. I need to get an x squared. How many times do I need to do it? 3 times. So I need to find 3 zeros. I need to do this 3 times. Okay? Is it possible 1 could be a 0 twice?
Yeah.
What does that factor look like if 1 is a 0 twice? How, if you solved it algebraically and you got something on the left is equal to something on the right and you're setting it equal to 0, what was on the left if I just wanted 1 to be my solution twice? No, this is my factor. If 1 is a solution twice, it's raised to an exponent of 2. Okay, this is called the multiplicity. Okay? If I end up with x minus 1 being one of my factors with no 2 there, it's got a multiplicity of 1. It's only a factor one time. If I have x minus 1 raised to the second power, it's got a multiplicity of 2. It's a 0 twice. I'm going to show you graphically what 2 zeros does to the graph. We're going to do that in a minute. But I just want you to know, just because you found 1 to be the 0 one time, doesn't mean it can't be it again. And if it is it again, if I want to divide it as a factor, it would be x minus 1 squared. It's going to have a degree of multiplicity of 2. Okay, so for the fun of it, I'm going to just try and see if it's possible that 1 is a 0 twice. Okay, so I'm going to see if 1 is a 0 twice for the fun of it, because 1 is the easiest number to do. I don't want to go all the way through 6 and not find another one and then realize I should have tried 1 again. Okay, so let's try 1 again. So all I'm going to do, I've already created my list. It's already there for me. I don't have to rewrite it. I'm going to try 1 again. Okay? Bring my 1 down. 1, negative 2, negative 2, negative 23, negative 23, negative 6, negative 6. I found another one. So 1 is actually a root or a 0 2 times, not just once. Now it's down to a cubic. I need it down to a quartic, or a quadratic. What's that? We could try 1 again, see if it's one. See if it's a root a third time.
Okay.
It could be. I'm going to put this up here. Whoops. Come on. So bring the 1 down. 1, negative 1, negative 1, negative 24, negative 24. I can see right now. Not going to work. Okay. So we try again. We're going to work our way now across the numbers. Negative 1 is another choice, right? 1, negative 1, negative 3. 3, negative 20. I can see before I finish it's not going to work. You're going to start doing this fast enough and be able to see. You don't need to complete it all the way through to see there's not going to be a remainder of 0.
About 2.
Okay, that's what we're going to do. We're going to work our way through the list. One, 2, 0, 0, negative 23. I'm done. It's not going to work. Negative 2. This is just an effort of persistence. Okay? Because I can't do anything until I get it down to a quadratic. So I'm going to go negative 2. Negative 2, negative 4, 8, negative 11? No. What is it? 15? And it's not going to work. 3. 1, 3, 1, 3. Negative 20? Nope.
Try negative 6.
Negative 6?
Yeah.
1, negative 6, negative 8, 48. 48 minus 23, 25. Nope. Let's try 6. We still have negative 3 to try, but we'll just do 6. 1, 6, 4, 24, 1, 6. There it is. Yep. So my zeros so far are 1, 1, and 6. That's 3 zeros. How would I describe this as a polynomial? What would it be? What's left? Tell me the polynomial. How would I describe this as a polynomial? What do these numbers mean? They're the coefficients of what?
The coefficients of 6. X.
Okay. We started with x to the 5th.
Oh, so
We got x to the 4th. There's x to the 3rd.
X to the squared.
So this is x squared plus 4x plus 1. Okay, I don't need to keep doing this with rational zeros. In fact, if I had done negative 3 and found it not to be a 0, there are no more rational zeros. That does not mean there are no more zeros. What are examples of irrational zeros?
Negatives.
Nope. What's an irrational? Fractions are rational. What's irrational mean? Square roots. Okay? Square roots. So, can I factor this? No. So I'm going to have to use quadratic formula. Okay? Negative b plus or minus the square root of b squared minus 4ac all over 2. Okay? 16 minus 4 is 12. How do I simplify the square root of 12?
It's 3.
2 squared is 3, right? Okay, so negative 4 over 2 is negative 2. And 2 squared to 3 over 2 is just the square root of 3.
That's 2 cancel out.
Yeah, 2 has to go into both to cancel out, though, not just 1.
Right.
Okay, so my answers now, my zeros, are 1, 1, 6, negative 2 plus or minus the square root of 3. I have 5 zeros. My problem was an x to the 5th problem. So you're going to have 5 zeros because that's the degree. Okay? If I want to write these as factors, this is x minus 1 squared times x minus 6 times x minus negative 2 plus or minus plus the square root of 3 and times x minus negative 2 minus the square root of 3. This is just a number if I put it in the calculator, right? And when you write a factor, it's always x minus whatever that number is. Okay, so that's how I would factor it. Okay, what I want to show you is what this graph looks like. Yep.
Multiplicity.
Okay, this is the graph. What did we say our zeros were? The first 3 that you remember.
1, 1, 6.
1, 1, and 6. Okay? So look what happened when it's just a single multiplicity. Okay, it goes straight through. No resistance. It's just going to go straight through at that point. But when it's got a multiplicity of 2, it comes up to the 1, and it turns back around. It doesn't go through. Okay? If I had a multiplicity of 3, it would go up, try to turn back around, but then end up going back up again. So it wouldn't go straight through. It's going to take a little detour and then can keep going through. Okay? The multiplicity tells you what the behavior is at that 0. Okay? If it's a multiplicity of 1, it just straight through. If it's a multiplicity of 2, it bounces. It hits the 0 and bounces back. Multiplicity of 3, it goes to the 0, tries to bounce back, and then ends up going back through. So it's going to kind of have a little flattened surface there at that 0. Okay, looking at a graph, you can tell what the multiplicity is by the graph. Okay, the other thing we found were the 2 other zeros, and I've just both of these were irrational. They were not fractions. They were not integers. If I put those in the calculator, 2 plus the square root of 3, 2 plus the square root of 3, it is 3.73. Negative, it was negative 2 plus the square root of 3. There's negative 3.73. 2 minus the square root of 3, or sorry, negative 2 minus the square root of 3. Negative 2 plus the square root of 3. negative 0.267. There it is. Okay, so this graph just reinforced the zeros I found. It told me I was correct. Because it had a multiplicity of 2, it had that bounce. Okay, so even though it looks like there are only 1, 2, 3, 4 zeros, because it bounced, you know the degree of this polynomial is 5 at minimum. If I had found negative or imaginary roots, okay, that would have been 2 more roots in there that I couldn't graph because they're imaginary. So the minimum degree of this polynomial is 5, but it's possible that I have imaginary roots, so it could have been an x to the 7th, an x to the 9th. Why couldn't it have been an x to the 6th?
Because you already have 6 on there.
I have 5 on there. Why couldn't I have added an x to the, why couldn't it just be 1 more 0?
Oh, because the exponent tells us that we have to have only 5 zeros.
No, I just said we could have more than 5 based on this graph. But the others would have to be imaginary. So why couldn't we have 6? And why would it have to be 7?
It has to be greater than the boundaries.
Think about the quadratic formula and how you get an imaginary solution. What's the sign in front of your imaginary number always? Plus or minus. Plus or minus. Imaginary roots always come in pairs. Irrational roots always come in pairs because when I put it in the quadratic formula, what's always before the radical sign? Plus or minus. So my possible solutions here are 5 or 7 or 9. I can't have 6. There's no way for me to get a single imaginary solution. They always come in pairs. There's no way for me to get a single irrational solution. They always come in pairs because there's always a plus or minus in front of the radical. That's really important to know. Never have a single imaginary or a single irrational root. They always come in pairs. Okay. Other things you should know. Let's go through the textbook check and then maybe try another example. Okay, looking at this polynomial, what's the minimum number of solutions you would expect? 6. Because of the degree is 6. If the square root of 3 is a solution, negative square root of 3 is also a solution. True. They always come in pairs. For it to be the square root of 3, it had to be plus or minus the square root of 3. Using the rational root theorem, 10/3 is possible here. Well, what are possible solutions or factors of 10? 2 and 5, 1 and 10. What are possible factors of 6? 2 and 3, 1 and 6. Okay? Is there any way for me to get a combination of 10 over 3? Yes. Because there's 10 here and 3 here is possible. So 10/3 is one of your possible rational solutions. I don't know if it is. We have to use synthetic division and figure it out. But it is possible based on the rational root theorem. You have graphed a polynomial, and the curve appears to touch the x-axis at -4 and change directions. This means that -4 is a repeated root, multiplicity of 2. How would you write that factor? X plus 4 squared. It's a repeated root, so the exponent's 2. What's the lowest possible degree of the polynomial below?
5.
Yeah, lowest possible. It could be more. But the minimum that it's going to be is an x to the 5th. Okay, do we want to do another example? Or do you want to just try it and...
Could be another example.
Okay. That's where I put my book. I'm going to do an x cubed. Stop. Okay, when you first look at a polynomial and they want you to find the solutions, ask yourself how many times you're going to have to do synthetic division to get down to a quadratic. Once. That's all I need. If I can find 1, 0, whatever I've got left will be a quadratic, and I know how to solve those. Okay, so I need to find my possibles. So minus 1 plus or minus 2 plus or minus 3 plus or minus 5 plus or minus 6 plus or minus seems like a lot, but it's much better than infinity. I mean, at least I'm not starting with the lowest fraction I can think of and working my way up. I know that this is the only possible list. And why don't I have it over a number? Why isn't it divided by a number? Because the leading coefficient is 1. If it was 2, I've got to be sure and put that in the denominator and give all my possibles. Okay? Let's pretend for a second it is 2. Because there's going to be a question on the quiz that just says list all possibles. You don't have to do anything else. You just have to find the possibles. Okay? So let's just pretend, for the sake of doing this problem, that there is a leading coefficient of 2. Okay? So my possibles are plus or minus 1, 2, exactly the way the numerator is written because it's divided by 1, right? So that's all my divided by 1 possibilities. Now I've got to go back and do all the divided by 2. So then I would have plus or minus 1/2. Plus or minus 2 over 2 is 1. I've already accounted for it. I don't have to write it again. Plus or minus 3/2. Plus or minus 5/2. I don't have to do 6 because 6/2 is 3 and it's accounted for. 10/2 I don't have to do. 5's accounted for. So all I have left is 15/2. So if you have a question on the quiz that says find all possible rational solutions, that's your answer. It's a long list, but that's how you do it. Okay? You don't have to do any more work than that. Just find the possibles. In years past, they see that problem and then they start doing synthetic division to find the actuals. That's not the question. The question is the possibles. Okay? But this is our list for this problem. Okay, so I'm going to start with 1. Do I have any that I need to skip? No, no placeholders. Okay, 1, 1, negative 1, negative 1, negative 16. Nope. Negative 1, 1, negative 1, negative 3, 3, negative 12, See how I'm finding, I can see early that it's not going to work? I don't want to have to go through this all the way through all these times. I just want to do it until I know it's not going to work and then try the next one. 2. So this is no. 1, 2, 0, 0, negative 15, negative 30. 1, 2, 0, 0, negative 15, negative 30. I got my 0. And I only had to do it once because it's a cubic. So how do I write this as a polynomial? What's the easiest way to solve this if there's no middle term? Yeah, just add 15 to the other side. Okay, let's just check it. if I graph this just real quick for the fun of checking my answers. X cubed minus 2x squared minus 15x plus 30. Okay, I said my zeros were 2 and then the square root of 15 plus or minus. Well, square root of 15 is 3.87, so it's going to be negative 3.87, positive 3.87. There it is. Okay, so I just confirmed. Now, how could you use a graphing calculator to help you get started in this process? Instead of going through all the numbers through 6 through 30, how could I have used the graphing calculator and started the problem first?
Plug in your possibles.
Well, I would have graphed my polynomial like this, and I can see one of the zeros is an actual rational integer, 2.
Oh.
So what I would have done is just use 2 in synthetic division, should have come up with 0 at the end, and now I've got my quadratic, and I didn't have to try 1, negative 1, negative 2, negative 30, negative 15, positive 50. I didn't have to do all a list. I can use the graph and figure out what 1 is. Now, if the other 2 don't fall on an integer, you know they're irrational. Well, they're potentially a fraction. But if I started with a cubic and I found 1, all I do is synthetic division with that 1, and I end up with my quadratic, and then I can solve it from there. I don't need to do a synthetic anymore. So sometimes the graphing at first can help you as a tool to find your zeros so that you can plug it into synthetic division and not have to try multiple numbers until you get one right. That makes sense. Okay. All right, so we've only got about 10 minutes, but work on some as you can so I can help you, and then we'll have more time in class tomorrow. Oh, 5 minutes?
Yeah.
Okay, we'll work on more in class tomorrow. Try some at home tonight.